Hi everyone, this is Kruti Pancholi, Assistant Professor in LG Institute of Engineering and Technology in Department of Electronics and Communication. You are watching videos of microwave engineering. We are going to discuss regarding the unit name, its analysis of microwave transmission lines and a waveguide. Over here, you will learn about transmission line equation. So friends, the question is, what is transmission line? So transmission line, that is a medium of transferring the power from the generating end to the load center. So conventionally, two-conductor transmission line, they are normally referred to as a transmitting microwave energy. So there are the kind of the transmission lines are there. So types of the transmission line, that are the open wire transmission line, coaxial transmission line, optical fiber link, okay. Then after the wave generators are there, okay. Then after the microwave strip lines are also available. So these are the various microwave transmission, various types of transmission line is here. So now, this over here in the diagram you can see, it is what? So it's a model of the transmission line which consists of the generating end, then the load end, okay, or the receiving end you can say. So generating end, then after the transmission line through they are connected, and then it is connected with the particular the coaxial lines, okay, or it is the microwave lines. So this way the transmission line is which will connect the generator to the particular load. So here in the diagram you can see that there is a generating end, the generating the particular the source is connected, okay, with that the some impedance is connected, and another one, the AA dash point, that is the generating end or the sending port number, and here in the diagram the BB dash, that is what? BB dash, that is the receiving end, and the load, that is the ZL is connected. So this transmission line that includes the two parallel wires, coaxial cables, microstrip line, optical fiber or the waveguide, etc. So it's a common diagram of the transmission line and how they connected with the source to the load. So now, to understand this, there is an important point, that is to get the idea about the transit time effect. Now in the first diagram, you can see that this diagram, that is for the lower frequency, that is the 50 Hz. You can see that the source that is connected and the signal which want to transmit it from the point A to point B. Okay. Now point A to point B, frequency is a 50 Hz. Now here in the diagram, the second diagram, you can see that, okay, while we are calculating the T value, so T is equal to 1 upon F. So 1 upon F, that is what? It's a 0.02 second. So now you can see that the sine waves that are shown for the 0.02 second. So we can see that, okay, while the length of the L, that is the transmission line, over here it is taken the path, okay. So point A, AA dash, while signal will travel from the point AA dash to point BB dash, okay. While the frequency, that is the very high, it will take a time, okay, it will take a time to reach that particular point. So that you can say that, okay, whatever the potential value that appear at the point A, okay, that is same as the point B. So if you will find out the potential difference, then the potential difference, that is 0 in that case. In the second diagram, for the high frequency, the source is connected and the signal to be transferred to the point B. So A point AA dash to point BB dash. Now here you can see that T is equal to 1 upon F. So if the value of the frequency is 1 gigahertz, it's a 10 raised to minus 9 second. So that is very faster change. So now if there is a faster change, so when the signal will travel from the point A to point B, so whatever the amount of the signal at the point A will not same onto the point B. So the value for the point A and point B, they are not same. So we can say that the PD is not zero in the potential difference, that is not zero. Here in the diagram also you can see that there is a faster change. So this way we can define that what is the transit time effect. So as we know that the time is equal to the length divided by the velocity. So suppose at the point A, the voltage, that is the Vp. Okay, at the point A the voltage is Vp. Fine. So here you can see the sinusoidal signal, the Vp and the Vq value that we can observe. So time is equal to the length of the wire or the velocity divided by the velocity with which the voltage travels. So voltage at the PB is a Vp. At the same time the voltage at the VAA dash, that is the VQ. Okay, so we have some potential difference. Okay, so that is why we can say that if the voltage at the AA dash, that is the VQ, at the output that we are observing, that is suppose VQ, then the potential difference is 0. But if the time it has taken to travel from the point A to point B, okay, there is some time, okay, is there, that is the length divided by the velocity, and due to that if the voltage at the 2 points are not same, then we found the potential difference. So that is why what is the transit time effect? That is time it has taken to travel, this length L is called the transit time. Okay, so what is the transit time effect? So transit time effect that we have learned that how to neglect the transit time. So transit time, that is by making the potential difference 0 or negligibly small, there is no transit time effect. So transit time effect we can neglect by making the PD 0 and negligibly small. Okay, so here you can see that suppose the T is equal to transit time period of signal. So T is much more greater than TR. But the TR is equal to L upon V. So by substituting this value in the equation, T, that is much more greater than L upon V. So what is a T? It's a 1 upon F. So 1 upon F much more greater than the L upon V. So now we'll interchange the V and F value. So V by F, that is much more greater than L. And we can say that what is a V upon F? V upon F, that is lambda. So lambda that much more greater than the L. So condition is wavelength should be much greater than the length. So that is the condition in the transit time. Now we are going to study about the transmission line, okay, for the microwave. So what are the primary constant of the transmission line that we need to understand? Here in the diagram you can see that the parallel wires that I can see. So it's a transmission line. Now I want to study about that small transmission line. So I am naming that a small segment as a delta Z. And which delta Z? That stands to 0. So now if I magnify this delta Z portion, so here you can see that this magnifying this delta Z component, we have the two values that is present on that line, that is the inductance and the resistance of that particular line. So here the wire length, okay, wire is suppose the R, okay, at a high frequency the inductance value, that is L between the wire, okay, at the high frequency there is a charge leakage, that charge leakage, there we will write as the G, and the capacitance value between the two parallel wire that we are assuming, that is the C. So here the transmission line model, you can see that the first diagram, that is the parallel wire representation. So two parallel wires are there. In the second, the differential section each delta Z long. So two wires divided, okay, the small portion that we are taking delta Z, and that delta Z, that is the tends to 0. Now, if we magnify it, that transmission line, then what we have, that there is always the leakage, so that we are saying that the some inductance value that may appear, okay, and the resistance of that wire between the two wire, okay, there is the G conductance, and between the two wire there is a capacitance that present, so that is the C. So if you will consider the small delta Z portion, then two delta Z portion that having the four primary constant, that are the R, L, G and C. So now if you will see the whole transmission line, then which will contain this many components. So it is important that the each section that are having this kind of the equivalent circuit, then we have to do the analysis of such kind of the transmission line model. So primary constant of the transmission line are the L, R, C and G. The unit of L, that is a Henry per meter, R is the unit, that is the ohm per meter, C is the Faraday per meter, and G, that is the inverse of the R. Okay, so we can write the ohm inverse or the mho per meter. So that is that. Now we need to calculate the transmission line equations. So transmission line equations, in that we need to consider the equivalent circuitry of the transmission line, which consists of the variety of the element. So now we are considering the delta L value, okay, of that particular part, okay. So the small segment, as I have shown the delta Z, okay, that we have considered. So now we are considering that portion. So now that particular the value R, okay, and it's a resistance value, okay. So R dash delta Z, L dash delta Z, that is the value of the inductance, okay, having the conductance value G dash delta Z, and the C dash delta Z, okay. So that are the values, okay, for the transmission line. To solve this transmission line, we need to apply the various Kirchhoff voltage law as well as the Kirchhoff current law, okay. So that over here we are applying the Kirchhoff voltage law, and we can write the V in into V out minus VR dash minus VL dash is equal to 0. Kirchhoff current law, that is the L in minus L out minus LG dash, okay, minus the LG dash, okay, IG dash, okay. So this way is equal to 0, okay. So we can note that the VL is equal to what? L di by dt, and IC is equal to C dV by dt. Okay. Also we know that the various cos theta and the sin theta value. What is the EZ component? So EZ is the EZ e raised to the j theta z. Okay. So we can also use the C is equal to A plus JB. Okay, that is the tends to theta, and it is equal to tan B upon A C, and it is equal to square root of A square plus B square. So now we are going to do the analysis by considering the particular the KVL and the KCL. Okay, so now for the first diagram, okay, which is given in the figure, okay, so it is what? It's a lumped element model, okay, and node A and the node B that you can see, and we can apply the various equations onto the node A as well as the node 2. So applying the Kirchhoff voltage law in the loop A, okay, so we can see that the sum of all the voltage status is equal to 0. So we can write the equation, okay, that is a V1 minus V2 minus V3 minus V4 is equal to 0. Similarly over here I can apply the KCL, Okay, so at the node B I am applying the KCL, and you can say that the sum of all the currents, okay, inside, outside, okay, so that is equal to 0. So I1 minus I2 minus I3 minus I4, that is equal to 0. Okay, so now we can also write the equation in terms of the variable, okay, that we have considered over here. So V of Zt minus R delta Z. Okay, what is that? V is equal to the IR. Okay, over here the impedance is there. Okay, so Vz of Z comma T minus R delta Z in bracket Z comma T minus L delta Z delta I Z T upon delta T minus V Z plus delta Z comma T is equal to 0. Similarly, for this we can apply that it is I of Z comma T minus G delta Z, okay, V of Z plus delta Z comma T minus C delta Z delta V in bracket Z plus delta Z comma T upon delta T minus I Z plus delta Z comma T, okay, is equal to 0. Okay, so now again more simplifying this equation and rearranging and dividing by the delta Z of the above equation. So now you can divide it by the delta Z and we can have the thing that is the delta Z that tends to 0. So by applying that limit to the equation, we can write the equation that is del of Vz upon delta Z is equal to minus R plus j omega L into Rz, and del d of Iz upon dz is equal to minus g plus j omega c V of Z. So this is about the first order equations, okay, of this. So now again we need to differentiate this equation with respect to Z. So by differentiating the equation with respect to Z, here you can write the second order differential equation. So in the first equation you can see that the d square Vz upon dz is equal to minus R plus j omega L d of Iz upon dz. For the KCL we can write d square Iz upon dz square is equal to minus g plus j omega c dvz upon dt. So this way we can find it out the equation for the second order, the differential equation. So now we can do the more simplification, and after simplification we write the equation and put the value that is of the gamma. So now from the equation you can see that what is the gamma? So I'll write that the gamma is equal to the propagation constant, which consists of all the values of the primary constant, and it is the square root of the R plus j omega G plus j omega C. So this way we can write the equation for the wave propagation in the plus z direction and the minus z direction. That is equal to Ve plus e raised to minus gamma z plus Ve minus e raised to plus gamma z. Similarly, for the Iz is equal to IE, okay, plus e raised to minus gamma z plus I. So Vz is equal to V0 plus e raised to minus gamma z plus V0 minus e raised to plus gamma z. Similarly, the Iz is equal to I0 plus e raised to minus gamma z plus I0 minus e raised to plus gamma z. So this way we have the propagation constant and the characteristics impedance that we need to find out. So e raised to plus gamma z, that's a wave propagation in the minus z direction, and e raised to minus gamma z, that is the wave propagation in the plus z direction. So that we can write the dvz by dz is equal to minus R plus j omega L into Iz. Gamma is equal to alpha plus j beta is equal to square root of R plus j omega L G plus j omega C. Alpha is the attenuation constant and unit is the meters per meter. Beta is the phase constant and radians per meter. So we can write the equation for the Iz, okay, and Iz is the gamma upon R plus j omega L in bracket V0 plus e raised to minus gamma z minus V0 minus e raised to gamma z. and I0 plus is equal to gamma upon R plus j omega L into V0 plus I0 minus is equal to minus gamma upon R plus j omega L V0 minus, where Z0 is equal to V0 plus upon I0 plus is equal to minus V0 minus upon I0 minus. So this way we can find it out the characteristics impedance Z0 is equal to R plus j omega L upon gamma is equal to square root of R plus j omega L upon G plus j omega C, unit is ohm, and lambda is equal to 2 pi upon beta. Vp is equal to the phase velocity is the omega upon beta is equal to 2 pi f upon beta is equal to delta f. So this is about the transmission line equation. So thank you very much everyone. You can see the LJIPT Electronics and Communication for more updates on the microwave engineering. Thank you very much everyone.